So since okay, since we got there, can we talk for a minute about your kind of your view on the status of the sort of smallest components? What can we, what can or should we say about the kind of how much of this kind of stuff, sort of the protocognitive kind of perspectives that we've been using, how much of that applies at the lowest scale? What can you say about particles versus their environment and so on?
Are you asking Chris or me?
Let's start with you, Joscha.
I suspect that the lowest level is not yet exerting interesting control, but it's just mechanical, in the same way as the vortex that emerges in the bathtub does not require intelligence to form. It's simply what's left over after you look at all the patterns and only retain those that are self-propagating. So it's basically, there's some selection process, some evolutionary process, if you want, that is selecting all the non-error correcting patterns from reality, and only those that are error correcting get to stay around with a certain probability. And once they are over the threshold, you can pretend that they are more or less static for a given time, and then you build structure above them. So I suspect that at the lowest level, you don't have intelligence yet. The intelligence only forms at the level where you have persistent particles that can be linked into symmetry breaking multi-stable structures, and then exploit like entropy gradients. So they basically, what life is doing, it performs controlled chemical reactions that outcompete dumb chemical reactions.
And what's the give me a ballpark of what do you think is the first / simplest thing that was doing that?
That's a very tricky question. I think the smallest structure is the cell, but it's not necessarily the simplest one, because the cell is incredibly complicated. I could imagine that you could have very, very large systems, say storm systems on Jupiter, that wake up into general intelligence before the first cell does, because the first cell is so complicated. I don't know what the assembly complexity of a cell really is, how likely it is for this first cell to randomly emerge. I could imagine that this probability is lower than the probability of a generally intelligent agent to emerge at much, much larger scales, of course. So in this sense, I don't know whether you will find spontaneously formations of agency at, say, planetary scales.
Yeah.
That we, of course, would miss from our cell-centric perspective. But I think that it's probably impossible to build intelligence simply only from elementary particles with, at the subatomic scale, because atoms are the first level, or molecules where you break symmetries.
What would you be looking for? So let's say the Jupiter spot or something like that. What would you be looking for?
I think that the timescales on Jupiter would be so large that it's almost pointless to figure this out. Ultimately, you would need to simulate it over very, very long time spans, and then basically see if the simulation deviates from a system that is energy optimizing in such a way that you need to assume that it has memory and is making models of the future to explain what you're observing.
Gotcha. Yeah, interesting. What do you think, Chris?
I agree that one needs a certain amount of complexity to think about planning for the future. I don't know where I wouldn't want to try to put a finger on where that complexity actually lives. Right? If you look at the kind of characteristic scale for, say, elementary particles not bound together in atoms, that characteristic energy scale is very large. And so what we at our scale and our observational capabilities call a particle is at that scale some kind of complicated mess. right? Think of drawing the first several orders of Feynman diagrams or something. There's a lot going on. And whether any of that stuff at its own scale could be interacting with other entities like that at that scale is hard for me to think about. Certainly, it's not something that we can observe with any technology that we have. So we're doing this business of calling things objects at a resolution that we can observe them, and then building a theory that maintains that sense of objecthood down to arbitrary scales. And that theory is predictive of what we can observe at our scale. But I don't know. I think it's more dangerous to say it's really describing what's going on at the scales that are of interest there. But certainly from the point of view of what can we observe, right? What are the kinds of intelligence that we can get a handle on? The cell or some set of coupled pathways that are bounded in some way is probably the smallest entity that we can think about. And maybe there are very large entities that have lower complexity. Again, the question is, how would we observe such a thing?
There's some really interesting work with minimal matter, so like droplets and things like this that are only a few chemicals, but they have some pretty rich behaviors, and I think we need to start developing sets of tools and kind of criteria for because just observations doesn't do the trick. Well, obviously you have to do some kind of perturbative experiments, but we really need to start trying to understand it, because yeah, some of them certainly look like there's a lot of potential for finding some of these things, and we need a suite of tests that can start giving us a clue that something like that is going on. The last set, they were they're running around a maze and they're coming together in multi sort of in higher order structures, and I asked them how long did you have to search? It's a total of, I believe, 3 chemicals that they're made of. And I said, how long did you have to search before you found the chemicals that do this? And he said, it's basically the first thing I picked up off the shelf. So my guess is that it might not be super rare, this kind of thing. And and it might be pretty natural, but it's unclear yet. I think the field of diverse intelligence still doesn't really have agreed upon criteria, like what to look for in these kind of systems, even for the ones that are tractable. I mean, obviously, they talk about the economics markets and the spot of Jupiter and the cosmic web and all these things. We can't do experiments there, but for some of these minimal active systems, we can. So I think we need to we need to settle on some experimental criteria.
No, that's very interesting.
Yeah.
I suspect that ultimately you might have to resort to simulations where you try to figure out the behavior of a system from first principles, and then run the simulation to see how your observations deviate, and identify criteria under which you need to ascribe more levels of control to the system that you're observing.
Yeah, I mean, we see this kind of very simple kinds of things in terms of going around barriers and kind of delayed gratification, where it has to go backwards in the gradient in order to get gains later on, and things like this in extremely simple systems. That emerges, that capacity emerges in even very you know, we studied it in simple sorting algorithms, you know, this ability to go backwards to make gains later on. You don't have to change anything, you know, very simple algorithms can have those behaviors. So I think we're going to end up with a lot of surprises, but we need to start looking for that stuff.
Yeah, ideally, one would have a way of looking at the system's ability to operate on its own environment for its own future benefit in some way. I mean, in a sense, with your algorithm experiments, the environment is us.
Yeah, I mean, there are these very minimal. There's a system which actually kind of mimics what real cells do, which is it constantly generates a self-repellent, and that just what that does is if you're traversing a maze and you end up at a dead end, you sort of sit there for a little bit, but eventually the self-repellent builds up and chases you out of there. And in practical terms, it means that you're never stuck in a dead end for any length of time. It pulls you out of these kind of cul-de-sacs where you can't do anything else, and it's super simple. And you can say that what you've done is you can look at it as a stigmergic effect on the environment, because you basically dumped a bunch of messages that 10 minutes later are going to say don't be here, go somewhere else. So it is a kind of a very weak version of niche construction from that in that sense.
Yeah, that sounds like a good limit to be pushing.
Yeah,
indeed.
Well, anyway,
is how to build a self-organizing system that is generally intelligent. Basically, what is the minimal pattern for this colonizing seed that we observe in our own mind? Basically, I suspect that consciousness is an operator that induces coherence. And I don't have a proper formalization for coherence that is that is properly tested. I think of it currently as a minimization of constraint violations across models. Could think of it as a consensus algorithm that is forming in the mind, and that is trying to find one interpretation where basically you maximize the number of simultaneously true statements in your working memory. And out of this would fall the notion that there must be an observer that is in the act of observation. But I suspect that the phenomenology of self-reflexivity comes from the fact that consciousness to work needs to be self-organizing, and to do that, it needs to be self-stabilizing and self-observing. And so basically, I wonder, what is this minimal self-observing observer that keeps itself stable and is colonizing the environment? What is the invariance, and how can we formalize it in a substrate agnostic way?
You want the informational analog of a microbial mat?
Well, no, of an organism. I want to have something that is more than a biofilm. I want something that imposes structure on itself. Maybe the microbial mat is the precursor. Basically, it's a sufficient substrate where you have self-interested local nodes that can are trainable into performing the computations that you want.